our lesson would be about moisture and atmospheric stability. But before we talk about atmospheric stability, let's talk about moisture and hydrologic cycle first. So as you can see here in the illustration, we have the hydrologic cycle. It's the continuous exchange of water among the oceans, the atmosphere, and the continents. This can have a great effect on our atmosphere or on our weather conditions. Now let's take a look at the different properties of water which can also affect atmospheric conditions. So water is the only liquid found at Earth's surface in large quantities. Water is also readily converted from one state of matter to another. So we have different phases of water. We have solid or iced. We have liquid water. And of course, we have water vapor or water in gas form. Then water solid phase, ice, is considered to be less dense than the liquid water. I'll show you later it's this property. Water also is considered to have high specific heat capacity, which I think we were able to discuss last time about specific heat capacity and how it affects the climate or how it affects the weather conditions. So I want you to look at this one. This would be the hydrogen bonds of water in ice. So let's take a look at an animation. Okay, so I want you to look at the animation for this one. So let's have water. Okay, let's have liquid water. Okay. As you can see here, as you increase the heat, water molecules will be moving faster and faster. So there's an increase in volume as you increase the heat. So we can say that water expands. But as you cool it down, let's observe what will happen to the water molecules. Specifically to the volume of the water. So let's try to cool it down. Okay, so you can now see that they are moving. Okay, let's have another one. Okay, you can now see that they are compressed. Okay. Yeah. So they will be compressed. So the volume decreased. However, cooling it further, let's take a look at this. Cooling it further after compressing or after contracting, you can see that they will expand. Okay, so I want you to look at this. So this is water at 0 degrees Celsius. Okay, this is water or ice water. When you try to cool it, I want you to pay attention on the molecules. When you try to heat it, they will compress there. But when you're cooling them again, they will expand. So that's a different property of water. Do you know that water is densest at 4 degrees Celsius? And then cooling it further, 4 degrees to 3 degrees to 0 degrees, it will actually expand. So water is the only liquid which has that property or which has that behavior. So let's go back to this one. Okay, so you can see here hydrogen bonds. So hydrogen bonds are formed if you have liquid water, then you are going to transform it to ice by cooling it down. But take note also that we have here hexagonal formation, or the hexagonal crystals of the water is responsible for its expansion when it's cooled down. So let's take a look at hydrogen bonds. These are attractive forces that exist between hydrogen atoms in one water molecule and oxygen atoms of any other water molecule. These also hold water molecules together to form ice. And in ice, they produce a rigid hexagonal network. So as I have mentioned, this is responsible for the expansion of water as you cool it down for 3 degrees Celsius and as you cool it further. Okay, so taking a look at this graph, as I have mentioned, looking at this, take note that water is densest at 4 degrees Celsius. Okay, looking at this, as water freezes, the hydrogen bonds push the water molecules farther apart from each other, increasing the intermolecular space, resulting in expansion. Okay, as you can see here, for liquid water, so they have less volume than ice. Molecules form stable hexagonal crystal lattice structure when they are forming ice. Okay, so we have stable hydrogen bonds. For the phase change of water, so as I have mentioned, it occurs in different phases. You have solid, liquid, and gas. So you have from solids to gas, it's sublimation. So this is just a review of phase change. From solid to liquid, of course, it's melting. From liquid to solid, it's freezing. And then from liquid to gas, it's evaporation. And then from gas to liquid, it's condensation. And we also have gas to solid, which is deposition. Okay, let's take a look at calorimetry. This one is related with your thermodynamics. Q, which is the quantity of heat, could either be absorbed or released depending on the phase change involved. So you can either have positive or negative ml, wherein Q is the quantity of heat, m is the mass, and then L is the latent heat of fusion or vaporization. If the change is from solid to liquid or liquid to solid, we are using the latent heat of fusion. But if the change is from liquid to gas and gas to liquid, we are using latent heat of vaporization. Okay, so taking a look at this, from solid to liquid, that's melting, that's also positive MLF. So that means energy is absorbed. So it's an endothermic process. Same with a transformation from liquid to gas, which is evaporation. So that is Q equals positive MLV. So endothermic process again, heat is absorbed. But if you have here from gas to liquid, that is condensation. So this should be negative MLV because it's releasing heat. So it's an exothermic process. Condensation is an exothermic process. And then from liquid to solid, that's freezing. Again, it's releasing heat, an exothermic process. So Q will become negative MLF. Okay, so that is phase change. So we have here the different melting points of different substances, but of course we are concerned about water. And then we have the latent heat of fusion, and then the boiling point of water, and then we also have the latent heat of vaporization. Again, latent heat of fusion, we use that for transformation from solid to liquid or liquid to solid. But latent heat of vaporization, a transformation from liquid to gas and gas to liquid. Okay, looking at the graph also, do you think there's a temperature change during phase change? Okay, there's no temperature change during phase change. So you can see here in the graph, we have a plateau here. Yeah, at 0 degrees Celsius, we have here either freezing or melting, but there's no change in temperature. The temperature absorbed or released would be about breaking the bonds or creating the bonds. And then it will increase its temperature here. But at 100 degrees Celsius again, there's no change in temperature during the phase change. Okay, take note of that. But during phase change, the temperature does not change. But the heat absorbed could break the bonds. And then if you have heat released, you will create the bonds. Okay, so let's talk about evaporation. So some applications of evaporation. Let's take a look at this. Okay, how is firewalking possible? What do you think? If fire walking is possible, the fire walkers are actually dipping their feet on water so that the energy transmitted to their feet will go first to water for the evaporation of water. That's why they have to walk very fast before all the water evaporates. Okay? And then also, why do dogs pant? Any idea? Okay. Dogs are actually panting because, unlike us, they do not have sweat glands. Okay, we are very lucky that we have sweat glands. How can we cool ourselves down if we don't have sweat glands? So parang baka ganyan ang itsura natin sa dogs. They are panting. Okay, they are panting because it's their natural cooling. It's for them to cool themselves so that the water in the water the water in their mouth will evaporate and will give them a cooling effect. Same with us. We have sweat glands to produce sweat, and then when that sweat evaporates, that's a natural cooling process of our body. Because evaporation, as we have mentioned, evaporation is an endothermic process. It absorbs heat from the environment, thus it's a cooling process with respect to the environment. Let's take a look at this. For example, you have here the layer of your skin, and then you have your sweat in this layer. That will evaporate. Okay, this layer will evaporate, and then where will it get the heat? It will get heat from this layer. So this layer is actually cooled down. So take note again that evaporation is an endothermic process. However, it's a cooling process. Okay, same reason why pigs love mud. Or bakit parang lagi silang, sa mga nag-aalaga ng baboy, kailangan lagi silang pinapaliguan. Because again, they don't have sweat glands also. So when the water covering their skin evaporates, so that's a way to cool themselves down. But condensation is a change of phase from gas to liquid. And take note, it's also known to be a warming process. Do you observe that before it rains, yung tinatawag nilang ang alinsangan naman ng panahon, yung sobrang init. So that happens because during condensation, it's releasing heat to the environment. It's an exothermic process. Therefore, it will warm the environment. That's why condensation is known to be a warming process. Steam burn is actually more damaging than a burn from boiling water because steam has higher energy compared to a boiling water. So, ganun din. Sometimes you observe if you are taking a hot shower and then, or yung warm bath, and then you observe that it condenses. So, it is very warm inside the shower room. Now, let's take a look at humidity. Because when we say humidity, water vapor present in air is very important. So, it's the general term used to describe the amount of water vapor in air. We have absolute humidity, mixing ratio, vapor pressure, relative humidity, and dew point. So we are going to discuss these terms. When we say absolute humidity, it is the mass of water vapor in a given volume of air. So again, mass of water vapor present per volume of air in cubic meters. Okay, next. How about mixing ratio? When we say mixing ratio, it's the mass of water vapor in a unit of air compared to the remaining mass of dry air. So in the formula, we have mass of water vapor in grams. Then the mass of dry air is in kilograms. Okay, as you can see here, so we have the mass of parcel or dry air, 1 kilogram. And then the mass of water vapor is 20 kilograms. The absolute humidity is 20 grams per meter cube. Because you can see here, this one has smaller volume. Okay, so there would be 20 grams here because of its smaller volume. So parang they are compressed in 1 meter cube. But absolute humidity here is less because this parcel of air has higher volume. Therefore, if you're going to look at 1 meter cube, there will be few water vapor present. But unlike for the mixing ratio, even though you have smaller volume of air here, or a smaller parcel of air, and then you have a higher volume of parcel of air here, mixing ratio are the same. Because mixing ratio is the mass of water vapor compared to the mass of dry air. So mixing ratio here is 20 grams per kilogram. So it's also the same, 20 grams per kilogram, even though you have different volumes of parcel of air. Take note of that. So more definitions. Vapor pressure is the part of the total atmospheric pressure attributable to its water vapor content. Okay, so we know that there is pressure in the atmosphere, but when we say vapor pressure, it's only attributed to the water vapor. It's not with the collision of other particles on air. Then when we have here saturation, air has reached equilibrium. Okay, when air is saturated, pressure exerted by the motion of the water vapor molecules is known as saturation vapor pressure. If air is saturated. Okay, let's define other terms like condensation nuclei. Condensation nuclei, they are tiny particles upon whose surfaces condensation of water vapor begins in the atmosphere. Diba? Dust particle. That's considered to be a condensation nuclei. Okay, next. Temperature and wind impact evaporation. The wind and warmer temperatures are actually enhancing evaporation. And also, temperature has an impact on condensation. Okay, of course, kapag windy, water could evaporate easily. And also, warmer temperature, that will enhance water vapor, or that will enhance evaporation. Okay, because it's a transformation from liquid to gas. Also, in condensation, as molecules in warm air are moving faster, pag meron silang na-meet na condensation nuclei, and then the warm air is moving fast, it will just bounce off. They will not attach to the condensation nuclei. Unlike slower moving molecules, if you have cooler air, that means the particles are moving at slower rate compared to warmer air. So there's a tendency that they will stick to the condensation nuclei and they will start to condense. Okay? So condensation occurs primarily when air is cooled. If you can see here, it's not a saturated air condition, so you have dry air. Then it has evaporation. It also has condensation. However, there are more water molecules which are evaporating than condensing because the air is dry. But if you have here, gauge records saturation vapor pressure for 20 degrees Celsius. If you have a saturated air at 20 degrees Celsius, the same number of water molecules are evaporating as are condensing. If you have higher temperature also, but it's saturated, the same number of water molecules are also evaporating as are condensing. Unlike kapag dry yung air. Okay, so you have here the saturation vapor pressure. Okay, you have here the saturation vapor pressure. We have at 20 degrees Celsius. Okay, the water vapor present is this. Yeah, grams per kilogram, as we have mentioned. Yung grams per kilogram, that is the mixing ratio. Saturation vapor pressure depends on air temperature. If there's an increase in temperature, there's also an increase in the number of molecules of water in the air, thus increasing saturation vapor pressure. Ganito yan ha, baka malito kayo. Siyempre, the higher the temperature, the higher will be the rate of evaporation, or more water can evaporate. That's why there's an increase in the number of molecules in the air. And it will increase the saturation vapor pressure. Okay? So yeah, at higher temperature, it takes more water vapor to saturate the air. Higher temperatures also means higher saturation vapor pressure. So dapat mas maraming water vapor ang present in the air. So mai-increase yung kanyang saturation vapor pressure. Okay, let's take a look at this. Balikan natin to. Saturation vapor pressure depends on air temperature. Increase in temperature increases the number of molecules of water in the air because nga, if you have higher temperature evaporation, there will be higher evaporation. Thus, there would be an increase in the number of water molecules in the air. And it will increase the saturation vapor pressure. At higher temperatures naman, it takes more water vapor to saturate the air. Kailangan mas marami pa rin water vapor present. So, higher temperature means higher saturation vapor pressure. Look at the relative humidity here. What is the factor affecting it? Temperature is held constant, para-parehong 25, 25, 25. But look at the relative humidity, it's 25%, 50% for this one, and 100%. So the factor affecting this would be the mass of water vapor present. Okay? So we have 5 grams here, 10 grams, 20 grams. The higher the mass of water vapor present at constant temperature, the higher is the relative humidity. Take note of that. So again, relative humidity is the ratio of water or the ratio of the amount of water vapor actually in the air to the maximum amount of water vapor required for its saturation. So a formula for this is water vapor content over the water vapor capacity, or you also have the vapor pressure over the saturation vapor pressure. It tells us how close the air is to being saturated. How about when there is a change in that temperature? How does water vapor content and temperature affects relative humidity? Nakita nyo na kanina sa illustration how water vapor content affects relative humidity. Let's take a look at how temperature affects relative humidity. So you can see here, what is held constant would be the mass of water vapor present. But you have different temperatures, 20, 10, and 0. Okay, let's compare this one. Ito, 20 and 10, because they have the same mass, 7 grams. If you're going to compare, the lower the temperature, the higher will be the relative humidity. Because, okay, again, as you can see here, the lower the temperature, the higher is the relative humidity if the mass of water vapor present in air is held constant. Okay, again, at the same temperature, an increase in water vapor content of the air increases relative humidity as the air approaches saturation. And if you hold the water vapor content constant, an increase naman in temperature causes a decrease in the relative humidity. Okay, temperature change. There are daily changes in the temperature. Temperature changes that result as air moves horizontally from one location to another. So, pwede yan because of the horizontal movement of air or because of the wind. Temperature changes cause as air moves vertically in the atmosphere. So, there could also be temperature change as you move higher to the atmosphere or as air moves vertically in the atmosphere. Now, let's talk about what is dew point temperature. This one is the temperature to which air needs to be cooled to reach saturation. Cooling below the dew point causes water vapor to condense as dew, fog, or clouds. So that is dew point temperature. Tandaan nyo yan ha. That is the temperature needed so that when you cool it further, it will condense. Saturation vapor pressure is temperature dependent. Okay, take note of this also. For every 10 degrees Celsius, the amount of water vapor needed for saturation doubles. As I have mentioned in the previous slides, the higher the temperature, the higher the water vapor present. But the higher also would be the water vapor present needed so that it will be saturated. High dew point means moist air, and low dew point indicate dry air. Because if you have dry air, the temperature should be colder so that it will condense. Unlike if you have moist air, even though it's at slightly higher temperature, it can condense because the air is moist. So hygrometer, it's one of the instruments that we can use to measure the moisture content of the air. The simplest one is a psychrometer, consisting of two identical thermometers mounted side by side. We will have a separate discussion on these instruments. Okay? So this is how it looks like. Meron siyang dalawang bulb. We have the wet bulb and then the dry bulb. Okay, what is adiabatic temperature change? The temperature changes without absorbing or releasing thermal energy or heat. So, paano yun? Therefore, how will it change? Kung hindi naman mag-absorb ng heat, hindi rin magre-release ng heat. Okay? When air is compressed, it warms. And when air is allowed to expand, it cools. Let's take a look at this animation so that it will be more clear. For example here, I will not add heat to the system, so I will not increase its temperature here, but I will try to compress this. We have here oxygen present in this container. Then I'll try to compress this one. I will not add heat, I will just compress it. So you can see that the temperature has actually increased. Okay, unlike when you allow it to expand, okay, the temperature decreased without adding heat to the system. You just compress and expand it. Okay, so you can see when air is compressed, it warms, but when air is allowed to expand, it cools. So you can see here also, we have a rising air parcel, expands and cools. So from 32 degrees Celsius, 22 degrees Celsius, 12, take note that our atmosphere is not confined. So water molecules can expand as they move at a higher altitude. So at first, this one has higher air pressure, and then this one has lower air pressure. Therefore, kapag lower ang air pressure, this has a tendency to expand. Hindi na sila masyadong compressed. That is for the rising air parcel, expands and cools. But for sinking air parcel is compressed and warms. Because as you move down, you have higher pressure at the lower altitude, so that means the particles will be more compressed. And then, if it's more compressed, therefore it will warm. Okay, so hopefully you are getting the concept. Again, let me repeat. The higher the altitude, the lower air pressure that you have. So if you have an air parcel na nagmo-move upward, hindi na siya magiging compressed masyado sa taas because of the lower air pressure. So it can expand. And as it expands, it cools. But when it sinks, at the lower altitude, mas taas yung pressure. So there's a tendency that the air will be compressed. Then if it's compressed, therefore it will warm. Or it will increase its temperature. Okay? So let's define more terms. We have dry adiabatic rate. That is the rate of cooling or heating applies only to unsaturated air. Kaya nga tinawag nating dry. So the air is unsaturated. Then we also have this term lifting condensation level. It is the altitude at which a parcel reaches saturation and begins to form clouds. Okay? So, tandaan nyo yan, lifting condensation level. The release of latent heat, when we say latent heat, it's the heat involved during phase change. The release of latent heat will slow down the rate of cooling. Okay, that is what we know as the wet adiabatic rate. Halimbawa, nasa taas na siya, nagko-condense na siya, it will release latent heat. Since nagre-release siya ng heat, nawawarm niya yung environment. As we have mentioned, exothermic process is a warming process. So, since nawawarm niya yung environment, na-slow down niya yung rate of cooling because it's adding heat to the environment. Okay? So, gets? Pag may question, tanong nyo agad sa Facebook group natin or sa comments. So, yun naman yung wet adiabatic rate if the air is saturated. So, looking at this, we have the dry adiabatic rate. The temperature of rising air drops at 10 degrees Celsius per 1,000 meters. So, from 32, umakyat siya ng 1,000 meters, nag-minus ng 10. That's why you have here 32 minus 10, that's 22. And then, 22 minus 10, that's 12. Okay? Tapos, 12 minus 10 ulit, nag-2 na ulit. 2 na siya. However, this is the condensation level. So, what happens here? We now have the wet adiabatic rate, wherein this time, the temperature will drop at 5 degrees Celsius per 1,000 meters. So, here, 2. So, that's minus 5. That's why you have negative 3 degrees Celsius. Then, another minus 5. That's why you have negative 8 degrees Celsius. Okay? So, dahil nandito na siya sa kanyang condensation level, wet adiabatic rate na siya. That's the rate of cooling at this point. Wet adiabatic rate varies from 5 degrees Celsius per 1,000 meters for air with high moisture content and 9 degrees Celsius per 1,000 meters for air with a low moisture content. Okay. Rising air cools at a faster dry adiabatic rate from the surface up to the lifting condensation level, at which point the slower wet adiabatic rate commences. Balikan natin to. So here, there's a faster cooling kapag dry adiabatic rate. But after the condensation level, yun na yung nag-slow down na yung cooling niya at a wet adiabatic rate. Okay? So there are also other processes that can lift the air. We have orographic lifting, wherein kapag meron yung mountain, the air is forced to rise over mountainous barriers. Okay? So, yan. Pag ganun yung air natin. So, it will lift the air because of the windward. Okay? The movement of wind. And then you have here for the leeward, you have dry air. We also have frontal wedging. Okay, frontal wedging, yung nagmi-meet yung warm fronts and cold fronts. Okay, fronts are formed when masses of warm and cold air collide. Warmer, less dense, of course, is forced over the cooler, denser air because less dense will float and then colder or denser air will sink. Convergence. It's a pile-up of horizontal air flow that results in an upward movement. So, yan naman, nagpa-pile up naman yung mga nagmo-move horizontally. That's why meron piling up, upward movement of air. It occurs also when an obstacle slows or restricts the horizontal airflow. That's convergence. We also have what we call localized convective lifting. If at this surface, you have unequal heating, halimbawa dito is vegetated, so hindi siya mabilis uminit. Unlike for this one, we have no vegetation or no plants here. So, it can increase its temperature at a faster rate. So, yun yung tinatawag nating rising thermal. Okay? Unequal surface heating causes localized pockets of air to rise because of their buoyancy. So, yan, part lang ng air yung nagra-rise. And it can form clouds over that region. Okay, now let's talk about stability of air. Stability is the property of air that describes its tendency to remain in its original position. When we say stable, hindi na siya yung akyat, bababa, or hindi na siya mabilis mag-float or mag-rise and then mag-sink. Okay? So, if it can still easily rise or sink, that is unstable. Okay, looking at this, ano yung absolute stability? Okay, absolute stability happens when the environmental lapse rate is less than the wet adiabatic rate. So, tingnan natin to. Ano yung environmental lapse rate niya? The environmental lapse rate is 5 degrees Celsius per 1,000 meters. Ang wet rate niya ay 6 degrees Celsius per 1,000 meters. So, you can see that the environmental lapse rate is less than the adiabatic wet rate. That's why we have the absolute stability. Ano nangyayari dito? So, you have here, at 20 degrees Celsius, pag sinabi natin environmental lapse rate, yun yung environment niya or the surrounding temperature. You have from 20 at 1,000 meters, minus 5. It's minus 5 again, minus 5, minus 5, minus 5. But looking at this, at dry rate, we have 10 degrees Celsius per 1,000. So you can see here, at 20 degrees Celsius, bababa siya ng 10 degrees Celsius. So it will become 10. So yan. This has lower temperature compared to this. And then at 0 naman, minus 10 ulit dahil sa dry adiabatic rate. So you have here minus 10 again, so 0 degrees Celsius. Rising air is 10 degrees cooler na siya. So kapag colder na yung rising air, it will no longer rise. Dahil nga, mas malamig na siya kumpara sa surrounding temperature. That's why, it will become stable. So, yan yung absolute stability. Okay, next. So, dito naman, dito na yung kanyang condensation level. So, what will be the decrease? Minus 6 na siya. So, from 0, minus 6, that will become negative 6. Then, from negative 6, minus 6, it will become negative 12. So, you can see nga that this air is colder than the environment. Okay. Therefore, it's the absolute stability. Okay, next. Okay, this is the illustration of absolute instability. But let's take a look at its definition first. Absolute instability happens when environmental lapse rate is greater than the dry adiabatic rate. Natin. The environmental lapse rate is 12 degrees Celsius per 1,000 meters. And then the adiabatic dry rate is 10 degrees Celsius per 1,000 meters. So you can see that this is higher compared to this. That's why we have absolute instability. Another one, the ascending parcel of air is always warmer than its environment and will continue to rise. It occurs most often during warmest months when solar heating is intense. Tingnan natin. So this is the environmental lapse rate, 12 degrees Celsius. So from 40 minus 12, you have 28. Minus 12, you have 16. Minus 12, you have 4. Minus 12, you have negative 8. Then looking at this, ito muna tayo sa dry rate. That's 10 degrees Celsius. So next start sa 40 minus 10, you have 30. Minus 10, you have 20. If you're going to compare this parcel of air, kumpara dito, this has higher temperature compared to the environment. Therefore, it will continue to rise. Okay, that's why this is absolute instability. At this condensation level, so you have now the wet rate. That's 6 degrees Celsius per 1,000 meters. So 20 minus 6 na siya, that's why you have 14. Minus 6, that's why you have 8. But still, this parcel of air is at a higher temperature kumpara dun sa surroundings or sa environment. That's why this one is unstable. Okay, so that's absolute instability. How about conditional instability? Let's take a look at the conditions. When we say conditional instability, when most air has an environmental lapse rate between the dry and wet adiabatic rates, then stable with respect to an unsaturated parcel of air, but unstable with respect to a saturated parcel of air. So here, yan yung environmental lapse rate, 9 degrees Celsius per 1,000 meters, which is in between. Dito nga sila. In between siya ng 10 degrees Celsius and 6 degrees Celsius. Okay, you can see here, 40 minus 10, 30. So this is still higher. Then you have minus 10 ulit. So this is colder na siya. But at the lifting condensation level, let's check. For this, minus 6 na. That's why you have 14. Comparing to this, higher temperature itong parcel of air. Then minus 6 again. So you have 8. Still at a higher temperature compared to this one. So the tendency is to move or to move at a higher altitude. So magra-rise up pa siya. Unlike at this condition na magbababa na siya. Okay, so stability is determined by measuring the temperature of the atmosphere at various heights, considering the environmental lapse rate. The column of air is unstable if air near the bottom of this layer is significantly warmer than the air aloft. So kasi nga, if we have warmer air, that means it will continue to rise. Air is stable when the temperature decreases gradually with increasing altitude. It is most stable when the temperature actually increases with height. So the higher the altitude, then the temperature increases. Pag instability naman is there would be intense solar heating, warming the lowermost layer of the atmosphere. Heating of the air mass from below as it passes over a warm surface. Ayan, pag meron tayong warm surface, tapos na-heat niya yung area na yon, it is heated, therefore the tendency is that it will rise. Then we have the general upward movement of air caused by orographic lifting, frontal wedging, and convergence. So because of those movement of air, nalilift din yung air or nagmo-move din upward. So it's unstable. So there is instability. And also, it happens if there is radiation cooling from cloud tops. So radiation cooling at a higher, diba, sa mas mataas na lugar, mas malamig. Therefore, dun sa mas layer niyang mababa, it will continue to rise. Okay? So stability, radiation cooling of Earth's surface after sunset. So, after sunset naman, mas cooler na yung surrounding temperature. Then, cooler na yung air. It will no longer rise. Di na siya magmo-move upward. The cooling of an air mass from below as it traverses a cold surface. Magkakaroon din ng stability. And then the general subsidence within an air column. If it's colder, so that means it will sink. So that is stability.